Hi everyone. Here we're going to talk more about minerals on the surface of the Earth versus inside of the Earth, as well as how minerals relate to our rock cycle. So we're going to be looking at the organization of minerals, comparing, contrasting different types of minerals, explaining how minerals fit into our rock cycle and actually make up our rock cycle, as well as looking at different types of igneous rock. So the most abundant elements in our crust on Earth, so just the crust, what we're talking about now is oxygen, silicon, and aluminum. Those are the three largest percentage of elements in our crust. The two largest by far are oxygen and silicon. So there's plenty of oxygen and silicon in Earth's crust. So when we're looking at minerals and classifying minerals into different types, we classify by the dominant anion. So we have silicates, oxides, sulfides, sulfates, halides, carbonates, and some others. For this class, we're mainly going to be looking at either silicates or non-silicates. So we will have silicates, or everything else would be a non-silicate. So our silicates make up most of our most of our minerals, excuse me. They're the largest group, the most important. More than 95% of our crust is made of silicate minerals, and almost 100% of mantle material is silicates. Non-silicates they only make up about 4%, but they are economically very important. So some of the minerals that are used in our economies, in our societies, are non-silicates. So quickly about the non-silicates before I get into more about the silicate minerals. Non-silicates, many are carbonates, so they are the primary constituents in both limestone and dolostone. The two most important carbonate materials are calcite and dolomite, so we will use those as examples in this class. Not many non-silicates, they have high economic value, so even though they only make up 4% of the minerals in our crust, they are often the more economically valuable minerals. So many of the metals that we use, iron, copper, as well as zinc and salt, are common non-silicate minerals that we do rely on in many economies in today's world. So they make up 4% of our minerals, but they are still very, very important. So our silicate minerals make up most of the minerals on Earth in the crust and in the mantle. Silicates are called silicates because they have the SiO4 anionic unit. We're going to get into just a brief review of chemistry here. Silicate minerals have what we call the silicate oxygen tetrahedron, or people just call it the silica tetrahedron. So what this is it's 4 oxygen atoms bonded to a silicon atom in the middle. So it's three-dimensional. There's a silicon in the middle, and there are 4 oxygen bonded on either side. So it can look sort of like a pyramid with a triangle base. So every silicate mineral has the silica tetrahedron as its building block. So then the differences are how these silicate tetrahedrons are then bonded together to each other. So just a little quick chemistry review. Anions are ions with a negative charge, which means that they have an extra electron because electrons are negatively charged. A cation is an ion with a positive charge. That means it's missing an electron. Electrons, remember, are negatively charged. So if it's missing one, it's going to have a positive charge. Opposite charges are attracted to each other. So ions with opposite charges will be attracted to each other. So silicate minerals are divided up by how the silica tetrahedrons then connect to each other. So the silica tetrahedrons share the outer oxygens. So remember, it's one silica in the middle, 4 oxygens connected to that on the outside. So how those oxygens then bond together depends on which type of silicate we're looking, or controls which type of silicate we consider that mineral to be. So I'm going to go through some examples, some possibilities of the different types of silicate minerals. So independent tetrahedra means that it's a type of silicate mineral that has independent silicate tetrahedras. So the oxygens are not shared. They're not linked together. So this would be an example of the atomic makeup. So these are the tetrahedrons. They are not connected to each other. That's why they're called independent. So these minerals are, some examples would be olivine, which is this very, very fun green mineral, or garnet. So these minerals do not have cleavage, so they do not break on in any specific direction. You'll notice, because they are not connected together atomically. So the next type of silicate mineral we consider to be the single chain tetrahedra. So that means that the tetrahedras are connected in chain-like patterns. So like this diagram over here, we see that it is a single chain of these silicate tetrahedras. These minerals will have 2 cleavage planes generally, so not just one, but actually 2, like this. And usually always they're bonded at right angles to each other. So with single chains, we can also have double chains. So double chain silicate minerals are when we have the 2 chains and then they are connected to each other. So it is double. They alternate, sharing 2 and 3 oxygens. So for example, this tetrahedra shares 3 oxygens. This tetrahedra shares 2. This one shares 3. This one shares 2. So these minerals often will be in the shape of a prism. So prismatic, crystals, and they usually have 2 cleavage planes, but they can vary significantly with the double chain silicate minerals. So this is an example. This is hornblende. So the next is sheet silicates. So sheet silicates, each tetrahedra shares 3 oxygens with other tetrahedra, and they are in 2-dimensional sheets. So what this does is it creates one plane of great cleavage. So this is mica, an example that breaks off in really clean, neat sheets, almost like pages in a book. You can lift up the really thin sheets of this mineral and break them apart. So this 2-dimensional sheet creates sheet silicates. We also have framework silicates, which is where all 4 oxygens are connected. So it is in 3D. All 4 of the oxygens are connected. They share, all of the oxygens are shared with other silicate tetrahedrons. So some examples are feldspars here. So here we have potassium feldspar and plagioclase feldspar. So it's going to have a setup, something like this, where all 4 oxygens are shared. So the importance in going over the different types of silicate structures is to understand the ratio of silica to oxygen, because as we bond more and more, the ratio changes. So for example, as we increase the number of oxygen ions that are shared, the percent of silicon in the mineral actually goes up. So here we're only sharing 1 or 2 oxygen. Here we're sharing 2 and 3 oxygen. Here each one is sharing 3 oxygen. So this means that in the sheet structure, there's more silicon compared to oxygen than there is in the single chain. So the ratio goes up. The percentage of silicon in your mineral increases the more that you're sharing your oxygen. So here is the minerals in Earth's crust. So not just the elements, but the actual minerals that make up Earth's crust. So most of Earth's crust is feldspar, either plagioclase or potassium feldspar. We have quite a bit of quartz, and then there is about 8% are non-silicates. So, let me go back, and this part, let me say this is going to be very important for next week when we're talking about igneous rock and how how elements form in magma. So I wanted to introduce it today. So let's think about how minerals relate to different geologic processes. So why do we care about minerals, essentially? Why do we spend so much time thinking about these building blocks? If we're just going to get into talking about rocks, this is geology, why are we looking at the little minerals? Minerals can give a lot of clues to how the rock was formed and also the history of the life of that rock. So most silicates are formed from magma or lava as it cools, and the different type of silicate mineral that is formed can tell us a lot about the setting in which that rock cooled. So the pressure, the temperature, how quickly it cooled, how long it lasted at a certain temperature before it began cooling. The presence of silicate minerals give us a lot of information about how that cooling occurred and where. We can also determine what features used to be present on Earth. So if we find a huge amount of halite and gypsum, for example, we can guess that there used to be seawater in that location. And then there's certain minerals like garnet, which is here. They form in metamorphism. And these minerals that form in metamorphism can tell us quite a bit about the pressure and temperature that certain rocks have undergone in their past. So minerals give us a lot of clues about the geologic history of the rocks in which they reside or in which they have formed. So rocks are made from minerals. All rocks are made up of minerals. Some contain a combination, like this, for example, is granite. This is made up of potassium feldspar, which is the pink. The black is hornblende, and then the white shiny is quartz. So there's 3 different minerals making up this granite. There are some rocks that are made up of only one mineral. Most of them, however, are a combination. So what is a rock? So we have 3 types of rocks on Earth. We have igneous, sedimentary, and metamorphic. So igneous rocks are formed by cooling magma or lava. So magma that is either underground or has reached the surface. As it cools and crystallizes and hardens, we form igneous rock. Sedimentary rock is formed by material that is deposited on the surface of the Earth. So it can be either deposited by water, by wind, by ice, but sedimentary rock is formed by deposition of different layers of sediment that then harden into rock layers. And metamorphic rock is igneous or sedimentary rock that it has been changed or metamorphized into metamorphic rock due to very, very, very high temperatures and very, very, very high pressures. So metamorphism is when rock undergoes very high temperature, very high pressure, and the rock physically changes into what we call metamorphic rock. So what is a rock? So by definition, a rock is coherent, meaning that it holds itself together. It doesn't fall apart like individual grains. It holds itself together. It is also naturally occurring, which means it forms naturally on Earth. And it is an aggregate of minerals. So it is a collection of minerals, mineral grains, pieces of minerals, or mineral crystals that are collected and attached together. So by definition, a rock is made up of minerals, it occurs naturally, and it holds itself together as a solid. So how do rocks hold themselves together? There's two different ways. So we have clastic rocks, and we also have crystalline rocks. So clastic rocks are when the rock forms a bit of what we call natural cement. So we have mineral material will actually fill in the space between different mineral grains and work like a cement. So with clastic rocks, we have different mineral grains, rock grains here in the pink, and then the bluish, or here the gray, is what we call the cement. It's actually mineral material that hardens there, fills in this space to create a solid clastic rock. Or we can have crystalline rock. So crystalline rock is where we have interlocking minerals growing. So the minerals grow and grow and grow until they can't grow anymore, and they are completely interlocked and solid. So here is a granite. We have some feldspar and some hornblende that has had a long time to grow, so they have completely interlocked, creating a solid piece of granite here. So rocks are either clastic or crystalline. So on our surface of the Earth, we can find rocks either in broken pieces, so pebbles, boulders, something that could be picked up and lifted off the surface of the Earth, or we find them as part of our bedrock, so still physically attached to the crust. So an outcrop, if you've ever heard of an outcrop, this is an example. This is where we have exposed bedrock. So this rock is still fully attached to the crust, unlike these pieces that have fallen and since rolling down. They're not connected anymore to the crust itself. This rock is an exposed piece of our bedrock. So usually bedrock is covered in vegetation, in dirt, in sand, in gravel, in water, or in a city, a town, a road. So we don't usually, when we're looking at the ground, we aren't usually seeing bedrock. We're seeing some broken pieces of the bedrock that are now resting on top of the surface of the Earth. When we classify our rocks, we look at how did the rock form. So how do we determine igneous, sedimentary, metamorphic? It's really, we're looking at the formation of the rock. So how did the rock form? Metamorphic rocks form deep underground. So metamorphic needs high pressure and high temperatures, which you can only get deep underground. Sedimentary rock always forms at the surface of the Earth because the sediment must be deposited on the surface for it to then create rock. Igneous rock forms when melted magma or molten rock rises up and cools. So the three different rock groups are separated by how the rock formed. So the history of the start of that rock determines which rock type the rock is. So when we look at classifying rocks, so we have a couple of things that we look at, similarly to how there are a couple of things we look at with minerals. So we look at the size and the shape of the individual grains. So the grains within the rock, are they equant, meaning all of the different grains within the rock are the same dimensions all around, same size, or inequant in that it's more variable. We also look at the composition, so the proportion of the different chemicals that make up the rock. So this also determines the type of minerals that will make up the rock, is what proportion of different chemicals are there. Then we look at the texture and the arrangement of the grain, so not just the size and the shape of the grain, but how are they aligned, how are they connected, and then layering. Are there visible layers within our rocks? So for rock grains, We can see here this is an example of very fine-grained rock, meaning it's very, very small, versus coarse-grained rock, meaning that the grains within the rock are very coarse. Equant grains, where they're all relatively the same size and shape. Inequant is where they are not at all the same size and shape within the rock. This is a rock that has striations or stripes. This would be important if you were trying to figure out what type of rock it is, to note that it has some black and white wavy stripes on it. You can also see on this rock here we have inequant grains, so they are not the same size and shape. Some are long and skinny, some look more rounded like a pebble, but they are relatively aligned. So they are sort of all in a line along this dashed red line here. These are some things that you would want to look at when you are trying to make note of a rock. So I also mentioned layering. So there can be layering in both sedimentary rock and metamorphic rock. It's a bit different. So in sedimentary rock, we see bedding, where layers were deposited one on top of the other. So we see these layers here, whereas in metamorphic rock, when we see layers, we call it foliation. It's not quite the same as being deposited in these flat layers. We're going to spend a lot of time later in the class on sedimentary and metamorphic rocks, so we'll get into this in more detail. But when you see layers like this of this scale, it can be very striking. It's very, very beautiful, super interesting to then understand what actually caused those stripes in the rock, which in a few weeks you will be able to do. So our crust, most of our crust is made of igneous rock. So about 95% of our crust is igneous rock. About 5% is sedimentary rock. However, if we look on the surface of the Earth, so not throughout the whole crust layer, but just the actual surface of the Earth, we actually have the majority of our surface is sedimentary rock. So sedimentary rock only exists on the very surface of the Earth, and it actually makes up 75% of Earth's surface. So our rock cycle, as an introduction before we get into the rock types in coming weeks, there's quite a bit that goes on in our rock cycle. So our rock cycle is the formation, the creation, and the destruction of different types of rocks. So at all of our plate boundaries, we have different pieces of the rock cycle occurring. So here we have mantle plume. So we have a mantle material rising up to the surface. This volcano is going to erupt lava, which will then solidify into igneous rock. Erosion on the surface is going to expose sediment. That sediment will eventually be carried down towards the ocean through rivers, through wind, and sedimentary rock will be able to form there as those layers of sediment are placed. Here we have subduction. So this is an oceanic, this is ocean crust, oceanic to continental plate boundary. So we have a convergent boundary here with subduction. So here, as we have this subduction, this is melting. That melt is going to rise up and is going to erupt in this volcanic arc as igneous rock again. So here we have collision. So this is an example of a convergent boundary between two continental plates. So remember that continental crust can never subduct. It is not dense enough. It is too buoyant. It will never ever subduct into the mantle. So when we have convergence of two continental plates is where we have huge mountain ranges. So for example, the Himalayas are formed from this collision. This very intense collision causes a huge amount of pressure, and it will also push some of the rocks further downward. So we will see metamorphism happening here. So we will have really high pressure, really high temperatures as these two pieces of crust are smashing into each other. So we will see metamorphism happening here. So we will be creating metamorphic rock from this crust material. So eventually there will be, if you look here, our mountain is a little larger. Eventually we will erode to the point where we will actually be able to see our metamorphic rock on the surface of the earth. So on these mountains, you will be able to see that metamorphic rock as it has already solidified. So here we have rifting. So this is where we have divergent boundaries. So divergent, the two continental crusts are moving apart. This will eventually cause a lot of thinning of the continental crust and will allow for the creation of an ocean and a spreading center here. But right now we have rifting, so these are moving apart. The high pressure of spreading this rock apart could create some metamorphic rock at the surface, as well as this mantle material is now going to be able to rise up into this thinner area of continental crust. So the mantle will be able to rise up. It will erupt as lava. It will solidify on the surface of the earth as igneous rock. So those are some examples of how formed at our different plate boundaries. So you can start to connect the plate boundaries to the different types of rock. We're going to go into a large amount of detail in the coming weeks about the different rock types. So this is just meant to be an introduction of our rock types. The transport of rock and the cycling of rock is very, very important. So most of the rock in our crust has actually cycled through our rock cycle many, many times. However, continental rock rarely returns to the mantle. Why? Remember that continental crust is not buoyant enough to subduct. The continental crust rarely ever returns back into the mantle to start this cycling over again. Oceanic rock, however, does follow a common cycle. So we would have a mid-ocean ridge where we have magma. That is going to eventually solidify into continental crust. That's going to solidify into oceanic crust, which will be an igneous rock, and then that igneous rock will subduct, and that subduction might cause some metamorphic rock due to very high pressures and temperatures, as well as magma, which will then rise up again and create igneous rock on the surface of the earth. So there's a lot of cycling on our earth, especially in the crust. What causes the cycling of rocks? It's mainly caused by the internal heat of Earth fueling plate tectonics, incoming heat from the sun causing our weather, which causes our erosion. So rain, wind, melt of snow causing rivers is going to erode and move sediment around. Gravity causing things to sink, to flow downwards, and then also life. So a lot of life can contribute to rocks breaking apart, breaking down, moving from place to place. So here is a very nice image of all sorts of geologic processes happening at once. Here we have rifting with our magma coming up to our volcano. We have some fault lines here, which we'll learn about later in class. Here we have deposition of material from this delta, which we're also going to learn about later in class. We're going to learn about glaciers, how glaciers affect our geology and our landscape. Here, this gray, I believe, is supposed to be metamorphic rock, so this would have been metamorphic mountains. Here we have our oceanic crust and our passive boundary, where we have the continental shelf extending out to the ocean. So we have a shift from continental crust to oceanic crust, but there's no plate boundary here. So this would be a passive margin rather than an active margin. So the cycling of our Earth, these four factors really keep our oceans, our crust, our mantle, and our asthenosphere moving and in motion, and also helps fuel this cycling by making portions of our system chemically reactive. So portions of our Earth will be chemically reactive in terms of reacting with water. Often helps fuel a lot of our cycling in terms of breaking rocks apart, allowing rocks to flow along down a river into smaller pieces, creating sediment, creating sedimentary rock. There's quite a bit that goes on in our rock cycle. So, a little summary of the introduction to the rock cycle, which we are going to spend many weeks on. So don't worry if you aren't getting all of the details today. Here we have our main components. So we have magma, igneous rock, sediment, so loose sediment, sedimentary rock, and metamorphic rock. So when we're talking about the rock cycle, we're talking about how these different components can turn into the others. So for example, magma solidifies into igneous rock. So if I were to fill in this rock cycle, here we have magma. Magma can cool and crystallize into igneous rock. Igneous rock then can be weathered away into sediment and then cemented and compacted into sedimentary rock, or igneous rock can undergo metamorphism with a huge amount of heat and pressure to create metamorphic rock. Sedimentary rock can also create metamorphic rock by undergoing metamorphism. Sedimentary rock can also create igneous rock by undergoing weathering to create sediment that can then be melted. So if either sediment or sedimentary rock is melted down into magma, that magma is then going to cool and crystallize again into igneous rock. So the same way that metamorphic rock can become igneous rock by heating, melting, and then solidifying into igneous rock. So the rock cycle, it's rather complex, but igneous, metamorphic, and sedimentary rock can each become another type of rock, depending on where it is, what type of situation it's undergoing. But the rock cycle on Earth is constantly cycling. We're constantly creating more of one type of rock from another type of rock, or melting and reforming igneous rock, heating and high pressure to create metamorphic rock, or weathering to create sediments, which will eventually compact into sedimentary rock. We are going to talk extensively about each element of the rock cycle in the coming weeks.